So I talk about this in 611 a little bit, but in this class I like to go into a little bit more detail. So this is a lecture, some material that you would normally cover in a VLSI design course, but we don't offer that course, or we haven't, at least for a while. So I like to touch on this in this class because it gives you an idea of why circuits are limited to certain performance, certain speeds. So semiconductors are built from silicon, and silicon being a semiconductor, it means it does not conduct electricity very well, but you can make it conduct electricity by putting dopants in it. So silicon forms a crystal, a lattice, where the silicon atoms form covalent bonds with 4 neighboring atoms. And they form those bonds at certain angles to make this repeating crystal structure. The repeating pattern in a crystal is called a unit cell. And if you take elements from, so silicon is in column 4 of the periodic table, means it has 4 valence electrons. If you take an element from column 3 of the periodic table, like gallium, for instance. This atom has 3 valence electrons, or boron, for instance. And you can dope the silicon with one of these elements, meaning that those elements will take the place of a silicon atom at certain points in the lattice. Now, the number of silicon atoms you're replacing with a dopant is determined by how much you dope it, how heavily you want to dope it. You dope it with these dopants, so you can use, column 3, like boron, which has only 3 electrons, or you can use one from column 5, like arsenic, which has 5 valence electrons. And what happens there is that when you replace some of these silicon atoms with this other element, this allows for charge carriers. So in the case of boron, boron has 1 less electron in its outer shell than silicon does. And so you've got this, like, basically a lack of an electron, which can actually move. The lack of an electron can move around in the lattice. So basically, what happens is that this boron has 3 valence electrons, and so it can get an electron from this neighboring silicon atom, in which case the lack of electron is transferred from the boron to the silicon. So it's what they call a hole. It's a lack of an electron. Likewise, if you decide instead to dope the silicon structure with a column 5 or group 5 element like arsenic, there's an extra electron in there because it has 5 electrons in its outer shell. And so likewise, that extra electron is able to move throughout the lattice. Okay, so whether you have holes that can move around or electrons that can move around, those act as charge carriers. So the thing that makes them move is current that you want to send through the semiconductor. And so these become charge carriers, kind of like, for example, like air doesn't conduct electricity. But if you hold up 2 ends of a wire with a large enough voltage potential between them and start making them, moving them closer and closer, eventually there'll be this arc of electricity that goes across. And what that arc really is it's the air ionizing between the 2 conductors. And that ionized pathway of air, that's the electrical arc, is the charge carriers, is actually what allows the electricity to flow. So you can ionize air to create charge carriers, or you can put these dopants in a silicon structure to create charge carriers. And by the more dopants you put in, the more heavily you dope the silicon, the better it conducts electricity. You get more charge carriers. The more charge carriers, the better of a conductor it is. Does that make sense? Okay, so, but the interesting thing is that when you put these dopants in and you get these charge carriers, whether electrons or holes, depending on which column of that you got the dopant from, those are referred to as the majority carriers. But there's also the other type of charge carrier that is opposite of, you know, the one that you deliberately doped with. So for instance, if you use arsenic here, you dope with arsenic, that's going to give you, that's column 5, that's going to give you electrons as the majority charge carriers. You also end up with minority carriers, some holes in there as well. Okay? So I'll revisit that here in a minute. Oh, by the way, this is the silicon unit cell. And so I forget how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, about 16, I think there's 16 atoms that are arranged in this unit cell at various angles. And then this unit cell is the repeating structure. It repeats over and over and over again. That's what forms the crystal. And so these atoms, by the way, are the distance between these atoms when these covalent bonds are formed is about 0.5 nanometer. That's how far apart they are. And the unit cell is about 5.5 nanometers. Now the reason that's a little remarkable is that if you think about the latest fabrication process that they have is like 7 nanometers, right? That's the smallest transistors you can get right now, 7 nanometers, and they're trying to shrink that down more. And you might think, well, how much more can they shrink that? Because the atomic spacing is 0.5 nanometer, and the unit cell is 5. I don't know if you have to have a whole unit cell at a minimum, but you certainly will need to have at least 0.5 nanometer. So you can. There's a very obvious, you know, limit to how far you can scale these down, unless you unless you move away from silicon. Okay, so. So you can build stuff with semiconductors like a PN junction is where the P-type silicon is where you dope it with the holes. So that would be the group 3. If you dope with an element from group 3, you're going to get holes as your majority charge carriers, and that's going to create P-type silicon, P standing for positive, and then positive meaning hole, lack of an electron. And then N-type silicon is when you dope with an element from group 5 where you get an extra electron. You get electrons as your majority charge carriers, and that gives you N-type silicon, N standing for negative. And so if you put them together, you get a diode where the P-type side is the anode, the N-type side is the cathode, and this will only allow current to flow in one direction from P to N, but not the other way around. Okay, and so now you might say, well, why is that? Well, the reason for that is because if you put a positive voltage on the P side, right? So you have a positive voltage of the P relative to N, and you have a negative voltage of N relative to P, right? So this is called a forward bias, where you've got a positive voltage on P relative to the N, and therefore you're trying to send current from P to N. The reason that works is because the majority charge carriers inside the P, and these are the holes. The holes get attracted to the junction between these two, right? And likewise, the majority charge carriers of the N-type, the electrons, they get attracted. So what ends up happening is the charge carriers move toward the junction, because this positive voltage attracts these electron charge carriers, right? And the negative voltage here is attracting the hole charge carriers, and the charge carriers kind of just meet up in the middle. And then that allows current to be conveyed from the P side to the N side. If, on the other hand, if you reverse bias, meaning that you just put the voltage of the N relative to the P is positive, right? What ends up happening here is that the positive voltage of the N side of the cathode is going to repulse the charge carriers, the the hole charge carriers away in the p-type side, right? Likewise, the negative voltage on the p side will push the electron charge carriers away from the junction. So basically, the charge carriers get pushed away. They kind of get pushed away from the junction, and so current will not flow in that direction. That makes sense? Okay, so now the problem is that we want to build transistors, and so those are like diodes, a little bit more complicated. So the idea with the transistor is that if you look at it, this is kind of a cutaway view, cross-sectional view, like a sandwich. You have a substrate. Substrate is, you could think of the substrate as what like the whole wafer is made out of, the whole chip, like the base of the chip, like the bottom part, like kind of like when you start out, you start out with a blank wafer, which is just silicon that's been doped, right? In this case, we're going to make it p-type, so we're going to put holes in there. We're going to put group 3 elements in there, right? Okay, and then you can create islands in there that are of the other type of silicon, the N-type silicon. Now, the way you do that is called diffusion. They have a process where you open up an opening where you want these are called diffusion areas. You open up an area here, and then you use gas. You expose the top of this to gas with the whatever the N-type dopant you want to put in there, and you make it very high temperature, and those elements penetrate. And so even if you start out with a p-type silicon base, a substrate, if you put enough N dopants in, it'll actually reverse the doping. So this would have originally been P, but now we're going to reverse it to become N to create these diffusion areas. You guys with me? So what you have now is this basically a little island of N-type silicon in a sea of P-type silicon, right? And so this obviously creates a diode. So these are connected. I mean, they're in contact, right? The substrate and the diffusion areas are just touching each other, right? So as long as the P substrate is grounded, you want to make sure that you keep the substrate grounded, because as long as the substrate stays at a lower voltage than the diffusion area, the ends, then no current will flow. These will become, you'll get that effect where the charge carriers move away from the junction between the diffusion area and the substrate, right? So all you got to do is keep the substrate grounded. As long as this has a lower voltage than the diffusion area, then they're basically not connected, even though they're right up against one another. They're not electrically connected, right? There's no connectivity there between those two. You guys with me? So you have these two diffusion areas, and in between the two diffusion areas is a little area of substrate. And the idea is that as a transistor, we want to be able to connect these two diffusion areas when we want to. We want to be able to electrically connect them, right? So that would be turning on the transistor. And that's going to be controlled by the gate. So the gate is this piece of silicon called polysilicon, which is it's a type of silicon that's the same type they make solar panels out of, essentially. It's this polysilicon. It's a very highly doped silicon. It's got good conductivity for silicon. And then you put in between that and the substrate, you have silicon dioxide, which is glass, and that's just a straight up insulator. You guys with me? Okay, so the idea is that we want to use the gate to turn on or turn off. We want to use the gate to be able to connect these two diffusion areas or disconnect them, right? Well, normally they're disconnected because remember the P is grounded, right? We want to keep the substrate grounded, and so the diffusion area and the substrate are disconnected. So how do we send current from one side of this structure to the other? How's that work? This is where it gets a little crazy. So basically, you've got P-type in the substrate. Majority charge carriers are holes, like this lack of an electron. And the N-type has the majority carriers are electrons. The gate is got a conductor with an insulator underneath of it, and then another conductor. So what does that form? That's a capacitor, right? And so if you put a positive voltage on the gate, and this is where it gets a little crazy. What we want to do is we want to attract the minority carriers out of this P silicon. Remember, the P silicon is positive, so there's holes. That's the majority carrier. But there's minority carriers, which are extra electrons in there. And if you put a positive voltage on the gate, it'll create a capacitor, a capacitive effect, where you'll have charge, right? So charge is the product of voltage and capacitance, right? So if you have a capacitor and you put a voltage on it, you get a charge. So you end up charging this gate. And that charge, that positive charge, will attract the electron charge carriers from the substrate. It attracts them to just below the gate into this, what's called a channel. The channel is a little thin layer of the substrate between the two diffusion areas, which are called the source and drain. Does that make sense? So you get this minority charge carrier. So you get minority charge carriers, which are electrons in the channel. The majority charge carriers in the diffusion areas, which are N-type, are already in there. And what you end up getting is the ability to send current from the drain to the source, right? So, because what happens is that the current flows from this diffusion area and it goes through the channel. And again, this is only when you have a charge on the gate attracting these minority charge carriers in the channel. You end up with you can conduct from the drain across the channel into the source. Make sense? So this creates an electric field that attracts these minority carriers. Now you might say, wait a minute, where did the minority carriers come from? I mean, when you doped it, you only doped it with column 3 elements, which are, they have 3 valence electrons, they have holes. I don't know, they're just there. You get them out of here, you get these minority charge carriers and they form this channel. That makes sense? So what you end up with is you can't go, current will not flow from the source or drain into the substrate, right? Because that would be reverse biased because the substrate is grounded. So you can't go from N to P, right? You won't have current from N to P. So these guys, these two diffusion areas are isolated, but when you have a positive voltage to create a positive charge on the gate, it attracts these electrons up into the channel, which creates a path. And so what you end up with is the ability to send current through the channel using these electrons as charge carriers. Make sense? And this would be this is an NMOS or an NFET. And the reason it's an NFET is because the diffusion areas are N-type, right? And then the body or the bulk or the substrate is P-type. The transistors are named after the type of silicon that you use for the source and drain. So this is an NMOS or an NFET or an N-channel, right? Same thing. That makes sense? Okay. Okay, so this is another picture of it. So this is an NMOS. You've got the gate, you've got the body or the substrate, and then the two diffusion areas. And then underneath the gate, directly underneath the gate, you have glass, which is insulator, and then below that glass, you have the channel. So I mentioned that there is a capacitor that is formed here between the gate, which is that polysilicon. It's basically, it used to be metal. I don't know if you guys, this is called a MOSFET. metal oxide semiconductor field effect transistor. So the MOS metal oxide semiconductor referred to metal oxide semiconductor, right? Except that's not metal anymore. They use poly for that now. Metal was the original way they built these. So now it's polysilicon oxide semiconductor, but they still call it a MOSFET. Make sense? And FET, the field effect, is referring to the electric field that's created by the capacitor here that forms the gate and the channel, between the gate and the channel. Okay? So we've got this capacitor here that between the gate and the channel, and we want that. That's actually there, well, it's part of the functionality. The reason it works is because you have a capacitor there, but also it's kind of unfortunate in a way too, because it's also what limits your switching speed, because the capacitor slows. It takes time to build up the charge. There's a time constant. So it's going to take time to turn this off or turn it on, and thus why chips are not faster than we want them to be. Likewise, there's also a capacitor too between the reverse biased diode that's formed between the diffusion area and the body. So you've got this reverse bias from N to P. That also ends up creating a capacitive effect there too. So these are not, I mentioned that the diffusion areas, which are the source and drain, they're not electrically connected to the substrate, but they have this capacitor. They form a capacitor. Make sense? Okay, so this is the same structure shown in 3 dimensions now. So this is kind of a sandwich, like cutting a sandwich, cross-sectional view. This is more of a 3-dimensional view. The important thing to note here is that the distance between the source and the drain, the source and the drain, these are the diffusion areas, is there's a parameter here called L, length, and that L is actually what they name CMOS processes after. So when you hear someone say, oh, that chip is a 11 nanometer process, or that's a 7 nanometer, oh, Intel can't get the 7 nanometer process working. We've been waiting 3 years. What was wrong with their fabrication? That's what that refers to as the L, the length. You want that L to be as small as possible, because the smaller your L is, the less distance the charge carriers have to travel when current is flowing between those. So there's 2 sources of timing here, right? As I mentioned, the gate takes time to charge because it's a capacitor. You got to charge this. You got to put a charge on this gate. That takes time. You got to get it charged up, and so that takes some time to turn on the gate. But also, once it's turned on, it also takes time for the current to traverse this channel. Now, some people think that this travels like at the speed of light. It doesn't. Charge carriers have something called mobility, which is basically how fast they move. And they don't move at the speed of light. They're actually kind of slow. So you want this to be as slow, this L needs to be as short as possible. This is why we're trying, the technology is always getting smaller, because we want this L to be smaller. However, on the other hand, there's a width, which is the other dimension. So the channel, I'm sorry, the gate and the channel, because the gate and the channel are the same size, because it's like a top and bottom of a sandwich. There's also a width, so you have a width and a length. The width shrinks at the same rate that the length does. So when you come out with a new, like Moore's law said that we double the number of transistors every 18 months or 2 years. That's how it used to work. So what that's referring to is actually the product of length and width, the area. So Moore's law says that the area of this length times width is halving every 18 months to 2 years. So it's not like the width, you might be saying, yeah, it's weird because they went from 90 nanometers to 130 nanometers, or what was it, 180 to 130 to 90 to 45. The length was not halving, right? But that's fine because it's the area that's halving, right, with Moore's law. But generally speaking, the length and the width, the minimum length and the minimum width are scaling down at the same rate. You guys with me? So if you reduce the length, if you go from one fabrication process to another and you reduce the length by a factor of, 0.3, then you're going to reduce the width by that same factor. However, you don't always want to have minimal width, because as long as the length is minimized, you might want to make some transistors wider, because the wider transistors allows you to have more current flow through here. And it allows this transistor to be stronger. It can drive more load. Okay, so sometimes, like if you want to drive a bigger load, like for example, when we talked about I2C and SPI, you had transistors ultimately that were driving those wires to go off chip. When you go off chip, there's a lot of load there because you got a lot of wire, a lot of capacitance, right? There's a lot of metal you have to charge and discharge when you're going off chip to long wires. And so those transistors will typically have a wider than minimal width, but the length will still be minimal, right? It'll still be whatever, 130 nanometers, 90 nanometers, whatever, 45 nanometers, whatever your fabrication process is, right? You guys with me? So you want the length to be minimized. The width can be minimized if you want to try to get the smallest transistors possible, but if you want power, then you got to go wider. Okay, so now here's the part of this that gets really confusing. The problem is that the gate voltage, so far I've just referred to it as the gate voltage, V sub G, right? But the problem is that whenever you measure voltage of one node relative to another node, right? So when you say V sub G, gate voltage, what does that really mean? What is it relative to, right? Well, you might say, well, it's relative to the channel, right? It's the voltage of the gate relative to the voltage of the channel, right? Because that's the capacitor, right? Those are the two ends of the capacitor, right? When you have a capacitor, you measure the voltage of one side of the capacitor to the other side. Yes, but the problem is, the tricky part, is that the channel is weird because it's not a traditional thing that you can measure. It's not, like, what is the voltage of the channel? Well, the voltage of the channel initially is going to be ground in this case, because I told you we ground the substrate and the channel is part of the substrate. But as the minority charge carriers start to collect in the channel now will start to become decoupled from the substrate, electrically decoupled. What will end up happening is that initially the channel is just part of the substrate, right? Because it's just all one piece of bulk silicon. But once you start getting those electrons to collect in the channel is no longer equivalent to the substrate. They're now becoming decoupled. So when you measure the voltage of the gate, what are we measuring it to? To the channel, right? But the channel voltage what is the channel voltage? Well, once you turn the transistor on, the channel voltage is actually kind of a gradient that starts, remember, because once you turn this transistor on and the channel activates and you start getting charge carriers, you've now decoupled the channel from the silicon, and now the channel is literally a connection between source and drain, right? So now you've got current flowing from actually drain to source in this case. By convention in the NMOS, the current flows from drain to source, although it doesn't, as you can see, they're symmetric, so it doesn't really matter. But anyway, you're sending current from drain to source, and that current, as it flows through the channel, now is creating a voltage difference between the gate and the channel that sort of is a gradient between the voltage of the gate relative to the drain and the voltage of the gate relative to the source, right? So what ends up happening is that the gate channel voltage is actually, when the transistor's on, is actually the average voltage between the gate and the drain and the gate and the source. So it's VGS plus VGD divided by 2, because this voltage will change depending on where you are in the gate, right? Because again, there's current flowing here, so your voltage here is different than your voltage here. It's kind of a gradient. As you move down the channel, the relative voltage between the gate and the channel, as you move down the gate, the relative voltage between the gate and the channel is now changing as current flows. And again, this is only when the transistor's on. When the transistor's off, then the channel is just ground, right? Because we ground the substrate to create a diode here, right? So that's the tricky part of this, is trying to figure out what is the gate voltage. It's hard to tell because it all depends on the state of the device. So the voltage between the drain and the source is when the transistor is on is the VGD plus VGS. And so you can reduce this down. The gate channel is going to be if you take this and you substitute it back in here, you just get the VGC is VGS minus VDS over 2. So now what we've done is we've said VGS, gate source, minus drain source divided by 2. Now what is this? What is the point of all this? Well, basically, when you look at the gate voltage, generally speaking, you look at VGS. When you evaluate the gate voltage on an NMOS, you're usually looking at VGS, or actually on a PMOS too. Either way, it's gate source. That's not gate channel, but gate source. That's generally the voltage you're looking at to determine whether the transistor is on or off. But then VDS, which is the total voltage you're dropping over the transistor, that becomes very important to figure out the operating mode of the transistor. So you care about that as well. So those are the two terms normally you look at, is the gate source voltage and the drain source voltage. Drain source being how much voltage you're trying to drop over the source and drain, right? Does that make sense? Okay, so those are the two terms the two terms you generally care about. Okay, so again, if the gate is 0, meaning that we've grounded the gate, right? Or yes.
Like I've seen these before with collectors and emitters. Is that the same thing?
Yeah, collectors and emitters are for bipolar transistors. They're for other
It's not the same as source.
Well, effectively they're the same thing. Yeah.
Are these like field effect transistors?
Yeah, these are field effect. Yeah, that's why. Yeah, so everything I'm showing today is MOSFET or in CMOS, which are the field effect. So if you ground the gate, or if the VGS is less than the threshold voltage, which is usually like 700 millivolts, then the transistor is off, right? So what you end up with is that you've got the source and drain, and it doesn't really matter what voltage you've got those at because the substrate voltage is ground, is at 0. So that creates a diode, a reverse bias diode the diode is from P to N, where P is the anode and N is the cathode. But because P is guaranteed to be at ground, you shouldn't be getting any current flowing from the substrate up, right? Or from the diffusion area down. It should be blocked, right? Nothing goes from the substrate up because the substrate's at ground, and nothing goes from the diffusion area down to the substrate because of the diode that's formed, right? So these guys get kind of just turned off, disconnected from the substrate electrically, and then the channel just has a different type of, it just has its holes in there. So, again, you have a diode basically created here, so there's no way to get current through the substrate because of the reverse bias diode that's formed when the transistor's off. When the transistor's on, and so generally in a digital system, typically when you turn it on, usually you're going to give it the VDD, which is like the power supply voltage, VDD. And so that will create this capacitor, and it'll create a channel, and that will basically electrically connect the source and drain. Okay, so we talked about this already in an earlier lecture. We talked about this. This slide's from an earlier lecture when we're talking about the push-pull drivers. So with an NMOS, this is the schematic signal. You've got the source, drain, and gate. There's actually a fourth terminal that's usually not shown. That's the substrate terminal or the bulk terminal, body terminal. In this case, that would be grounded, right? But that's not shown here. So when the gate is on, you connect. When the gate is off, you disconnect. Right? That makes sense, right? The problem is there's another type of transistor called the PMOS, which is opposite. But you know it's opposite because of this bubble on the gate. So when the gate is 0, you turn on. When the gate is 1, you turn off. So it works in reverse. And so the PMOS is actually the way you build it. See, the problem with the PMOS is you have to have the P diffusion area now, right? But the problem is the substrate was already P. So how do we how do we ensure that the diffusion area is different from the substrate if our diffusion area has to be P and our substrate's already P? The way you do that is you create a well. So you create a deeper diffusion area that covers the whole transistor. And then inside that diffusion area, you then create other diffusion areas, smaller diffusion areas. So this way you can have a little localized N substrate, and then you can put your P's in there to form the PMOS source and drain. You guys with me? Okay, so now here's the issue though. In the case of a PMOS, remember I said over here with the NMOS you had to ground the substrate to create these, to make sure that the source and drain weren't going to connect electrically to the substrate. In the case of a PMOS, you have this N well, but you have to do the opposite. You have to bring the N well up to VDD, because you want to create you want to make sure that no current flows across the channel or flows from the diffusion area. Flows across the channel when it's off, when the transistor's off. And you don't want to have any current flowing between the diffusion areas and its little well, which is its localized area of substrate. So if you take the N and you bring the N well up to VDD, then you know that the N is a higher voltage potential than P, or this N well has a higher voltage potential than this P diffusion area, and so it'll reverse bias that diode. Make sense? Okay. The question is, how do you do that? And for that matter, how do you ground the substrate, the regular substrate for the NMOS? Okay, so this part is a little weird, but the way that they do that generally is, notice that this says P and this says P plus, right? And this says N and this says N plus. The difference there is, remember, you can when you do your diffusion, when you create your diffusion areas, you can dope with different levels. You can do different levels of doping. The more doping you add, the more atoms in the silicon lattice you're replacing with the dopant atoms. And you also make the silicon more conductive because you're adding more majority charge carriers when you do that. So usually the way they set this up is, if you want to energize a substrate, you want to bring this N well up to VDD, it's done through a step where you first connect to an N plus diffusion area, which makes it easier to then inject into the N well that's less diffused. Same thing over here. Like the substrate has these P plus diffusion area that's used to increase the contact between the ground, which ultimately comes from a wire. So this would be a wire. This is going to be a metal wire. Is going to connect down to this very heavily doped P silicon, which then is butted up against this regular P substrate and creates a better electrical connection there. So that's not really super important, but that's the way that you either ground the substrate, the P substrate, or you set the N well to VDD. Okay, so that's individual transistors. How do you use those to build logic gates? Because that's the objective. Okay, so to build a logic gate, use CMOS logic, which stands for complementary metal oxide semiconductor. And the idea with that is you use for every input into the logic gate. So you guys remember, like, in 211, you had like AND gates and OR gates, and they had like 2 input, 3 input, 4 input. So for each input into the gate, you have exactly 1 PMOS and 1 NMOS. So if you have a gate with 2 inputs, that means there's going to be 4 total transistors. There's going to be 2 of each type, and they're balanced. So you have two transistors for each input, and the PMOS is used is the pull-up network, and the NMOS transistor is used for the pull-down network. So the idea is that for whatever input combination you send into here, you will either be creating a path through the pull-up network or a path through the pull-down network, but never at the same time. So this is the same thing we talked about with the push-pull drivers when we were talking about SPI. you're always going to be shorting the output of the gate to the power supply, or shorting it to ground, depending on what inputs you're putting in. But they're mutually exclusive. There's always going to be one of these guys on at one time. Make sense? Now you always use the PMOS for the pull up, and you always use the NMOS transistors in the pull down. Why? Why is that? Well, it turns out that PMOS are better at pulling up to VDD, and NMOS are better. When I say better, I mean faster. All right, they're faster because when you're using PMOS to connect to VDD, to short an output to VDD, they have lower equivalent resistance when you're pulling up. And likewise, when you're pulling down to ground, you want to use NMOS because they have lower equivalent resistance for pulling down. Does that make sense? So every logic gate then is separated into a pull-up network and a pull-down network, where the pull-up network are PMOS transistors, or PFETs, whatever you want, P-type transistors, and you've got the pull-down network, which are comprised of the NMOS, or NFET, or N-type transistors. Okay? Question is, how do you connect them together? How do you wire up the transistors? Well, that's what's going to differentiate one logic gate from another. Okay, so we talked about this one already. This is the inverter. With the inverter, it's real simple. There's only one input, so you just have two transistors. There's one pull-up and one pull-down. The gates of both are just both connected to the single input. So you just have A as the input, and it's connected to the gates. The gates of the transistors are generally regarded as inputs, right? The outputs are going to be, the output is connected to the middle, the wire between the pull-up and pull-down networks. So if A is 0, it's going to turn on this transistor and off that transistor, and so this Y will get a low impedance path to VDD and a high impedance path to ground, because when you turn on a transistor, it effectively, makes it have low resistance from source to drain. And when a transistor off, it has a very high resistance from source to drain, tens of mega ohms, right? So basically, if you put a 0 in here, you pull the output to 1, and if you put a 1 in here, you pull it down to ground. And again, that's because the NMOS turns on with 1, and the PMOS turns on with 0. That make sense? So this is the same thing we looked at with the push-pull drivers, because drivers are usually built, they're a driver, in other words, an amplifier, a circuit that you want to be able to amplify a Boolean value, a digital value, are usually built as an inverter. If you want to build something with more than one input, like a NAND gate, then, now this is where it gets a little weird. You've got the pull-down network have two transistors, NMOSs, connected in series, and the pull-up network are two PMOSs that are connected in parallel. Well, why is that? Well, this is what creates the logic, because if the inputs are both 1, then it'll turn both of these NMOSs on and short Y to ground, right? And then, of course, it'll turn both PMOSs off, right? So that makes sense, right? So a NAND gate gives you, it's not AND, it's NAND. It's the complement of AND. So in order to get a true output, you have to have, the inputs both have to be, in order to get a false output, both inputs have to be 1. Make sense? Right? So the truth table is, if you got 1 and 1, 1 and 1, A and B are 1 and 1, the output is 0. Okay? Any other input combination, though, will give you a 1 output. Why? Well, that's because these two guys are in, the pull-down network are in series. The only way to pull down is to have both transistors in series turned on at the same time. If either A or B is 0, then it will turn off one of the two transistors in series, which means it'll disconnect the pull-down network. But because the PMOSs up here are in parallel, if either one of these are on, in other words, if either input are 0, then it will be enough to turn on at least one of these two pull-up transistors and pull the output up to VDD. Make sense? All right. You might say, wait a minute, okay, but why NAND? Why not AND? Because we learned about AND gates in 211. Why can't you build just an AND gate? Why does it have to be a NAND gate? Well, the reason for that is because, think about this a second. Okay, so in order to pull down, like in other words, in order for the output to be 0, you have to be able to turn on at least one NMOS, NFET, and N-type transistor, right? Does that make sense? Okay, and also likewise, to pull up to have a 1 output, you have to have at least one of these guys turned on. And remember, to turn these guys on, you have to have 0. So at least one of the inputs has to be 0 in order to pull the output up to VDD, to be 1, right? Make sense? You have to have at least one input 0 to pull up. And you have to have at least one input to be 1 to pull down, right? Well, if you think about an AND gate, the AND gate is only true if both inputs are 1, right? Well, if that's the case, that's impossible, right? Because there's no way to build an AND gate here, because in order to physically generate a true output from this gate, you have to have at least one 0 input. But AND doesn't have that. AND doesn't allow you to have a 0 input and have its output be true, right? And so because there's no zeros in an AND gate to pull it up, there's no 0 inputs, right? Then it's impossible to build an AND gate with CMOS logic. You might say, well, someone's built one, right? Well, yeah, I mean, the way you build it is you have to take an AND gate and then add an inverter on the output, right? You can't build an AND gate with a single CMOS gate. You have to build a 2 gates together to realize an AND gate. You know, you can add an inverter to this, but then you have 2 gates. It's not 1 gate, right? OR is the same way, right? Or with an OR gate, you can't build an OR gate either with CMOS, because an OR gate, in order to have a 0 output, you have to have at least 1, 1, right? But with an OR gate, if you have 1, 1, it will never be 0. Right? If you put a 1 into an OR gate, you will never get a 0 output, because as long as one input is 1 with an OR gate, you're going to get a true output. And so that doesn't work either, right? Because there's no way to turn on, there's no way to pull down if you don't have any rows in the truth table that have a true output and at least there's no rows in an OR gate where you have a 0 output with at least one input to pull down. Does that make sense? Okay, so you can build a NOR gate though. So in this case, it's just kind of the reverse. In this case, you have, this has A, B, and C. That's a 3 input. Okay, so yeah, that's fine. So here's a 3 input NOR gate. You can build a 3 input. In this case, you have the pull up transistors in series and the pull down transistors in parallel. But in this case, because we have 3 inputs, there's 6 total transistors. And so in this case, in order for a NOR to be true, you have to have 0, 0, 0. All 3 of these guys have to be 0, which will create a path through these 3 transistors in series, and it will likewise turn off all 3 transistors in parallel, right? But if at least one of the inputs is 1, then that'll be enough to pull down to 0 and disconnect to the series of 3 transistors there. Okay, Does that make sense? Okay, so we talked about, I kind of brushed through this a little bit. I want to talk a little bit more detail about how these work. So I mentioned that the key to making these transistors work is this capacitor that's formed between the gate and the channel, and they're split with the silicon dioxide. And by the way, silicon dioxide is like beach sand, right, or glass, right? It's silicon, it's one silicon atom and two oxygen atoms, SiO2. It's strange. Well, not strange, but silicon dioxide does not conduct electricity at all, right? Because it forms a crystal, but there's no opportunity for charge carriers to move through it, right? If you have pure silicon, then you have charge carriers that can move throughout the lattice, right? But it's a little confusing because it's like, well, why does, because otherwise you think, well, either, silicon dioxide's pure insulator, silicon is a semiconductor, and then you've got the polysilicon, which is, it's just regular. It's silicon, but it has a very high doping to make it as conductive as possible. And like I said, they used to use metal for the gate back in the original CMOS transistors. I don't know exactly what the poly is. There's some benefit to using poly instead of metal for the gate. So so you got the polysilicon gate, you got this insulator, and then you got the body. If the gate voltage is lower than a certain threshold, which is V sub T, then the transistor is in what's called accumulation mode, which means the body is filled with majority carriers. Again, the P-type body, P is positive, so you got all these positive little plus signs in here. These are holes. And there's no current that flows. Now, when the gate voltage is between ground and VT, meaning that it's less than the threshold, what ends up happening there is you go into you get this thing called the depletion region, which is where the majority charge carriers start to back off from the channel. They start to get repulsed. And because it's because this electric field starts to form, and that electric field takes these charge carriers and moves them down, right? So the channel ends up becoming decoupled from the substrate, from the bulk, but it's not enough to attract the electrons in there to form the channel. Okay, but then when the gate voltage exceeds the threshold voltage, that's when you go into you get this inversion region, which is where the minority charge carriers, the electrons, collect in the channel there, and beneath those is a depletion region, so you get this, the substrate becomes electrically decoupled from the channel because of the depletion region, and the channel itself basically becomes kind of one electrically with the source and drain, because you have the same charge carriers in there as you do the source and drain, right? And that's called the inversion region. The problem, though, is, as I mentioned, that the channel, once that happens, the channel is no longer the same electrically. It's no longer connected to the substrate, the body of the transistor. It becomes its own thing. It becomes decoupled. And that's the reason why, by the way, you have to start regarding the voltage of the channel as being the average voltage between the gate and the source and the gate and the drain. So you end up with this average voltage inside the channel. It's no longer just ground. You're not referenced, the channel, the gate is not referenced to ground anymore. The gate is being referenced to the inversion region, which is this charge carriers that are being pulled up. So you end up with, I already covered this, I think. You end up with the voltage here. Now in this case, with an NFET or NMOS, the current is flowing from, is generally going to be flowing from the source to the drain. And it's the opposite for the PMOS. I always have trouble remembering that though for some reason. Yeah, the source is the terminal at the lower voltage. So I'm sorry, it's drain to source then. Sorry, drain to source. That's for the N type. For the P type, it's the reverse. So when you build your gates, okay, so here's the gate. When you build these gates, on the pull-down network, the drain is the one that's, notice that the drain is connected to ground. Sorry, I screwed that up again. The source is connected to ground. I always get this confused. It's the source is connected to ground. That's the bottom terminal of the NMOS. You guys with me? And then the drain is connected to, in this case, to the output, to Y, the output of the gate. Now, if you look at the pull-up network, though, the source is going to be connected, on this guy, the source is connected to VDD, and the drain isn't connected to the output because the drain is actually connected to the source of the next transistor because these guys are in series. Does that make sense? So you might say, okay, what's your point? My point is that when you're measuring the gate voltage, it's gate source, right? You want it to be relative to ground because that would make things a lot more easy to understand, but it's not ground. It's the source. Well, what's the source? Well, it just so happens in this case the source is connected to ground, right? So that's nice, right? The problem is, but that's just for these guys. When you look at the PMOS, in the PMOS it's reversed. So the gate is relative to the source. In this case, the source is VDD, right? So what's happening here is that when you set the input to this guy to 0, what you're really doing is creating a negative voltage, right? Because you're measuring the gate versus the source. Well, the source is at VDD. So if the gate is at 0 and the source is at VDD, you're putting negative VDD into this, right? But that's the way the PMOS actually works that way. It's the negative. Do I have a picture of the? I don't have a picture of the PMOS. Yeah, I do, right here. Yeah, so in the PMOS, you've got the N is the substrate, which is actually, as I showed before, it's actually a well, not the substrate. And then the diffusion area is P. So what do you have to do here? You got to put a negative voltage on the gate. So you get negative charge here, and then the N, you attract the holes. The minority carriers here are holes that get attracted to the channel. So you got negative voltage here to get a positive charge carriers down here on the other side of the capacitor plate. On the other side of the capacitor, on the other capacitor plate, the other side of the capacitor. You guys with me? So it's not really that you're putting when you put a 0 in to turn on a PMOS, you're not just putting 0 in, you're actually putting a negative voltage that exceeds the threshold voltage in terms of its magnitude. So the threshold voltage here will be like negative 700 millivolts. If I put a 0 in here and the source is at VDD, I'm actually putting negative VDD on this gate, right? Which is in excess of the, it's lower than the threshold voltage, and that's what will turn on the transistor. Does that make sense? Okay, so the point here is that it's gate source voltage that you use to determine whether the transistor is on or not. Okay, so all right, so in an NMOS transistor, then, if the gate source voltage is 0, okay, so again, gate source voltage 0, it's cut off, it's turned off. Right? If the gate source voltage is greater than threshold, okay, then you will, once it hits threshold, right, it goes into linear mode. So it turns on, and what happens is that once it turns on, the transistor starts to act like a resistor, because the current from drain to source starts to increase with the voltage between the drain and source. So it acts like it starts acting linearly, right? And so that's because you get this, you get the channel forming there, right? Now the problem is that the problem here is that if the transistor is on, but you try to draw, you start increasing the voltage over the source drain voltage. Okay, and you might say, well, why would you do that? Under what circumstances would that happen? That's if you're loading the transistor down. You're asking for more and more current. So and you might say, well, wait, how do you load it down? Well, okay, let me back up here again. Let me put this into a little perspective. Okay, if you look at this design, here's the Y. Y is the output, right? I'm not showing a load on here, right? Y is connected to nothing, right? And so this gate will just basically, when you turn on the PMOS, it's going to pull Y up to VDD, and so what that'll do is Y will be at VDD, right? And the other side's at VDD. So there's very little voltage drop here, right? Likewise, same thing happens here. If I turn on this NMOS transistor, it's going to pull Y down to ground, and so Y's at ground and that's at ground. That means the source and drain are both at ground, right? So there's no voltage drop, so no problemo, right? The problem though is that in reality, the Y is not going to be sitting there connected to nothing. It's going to be driving somebody. It's going to be connected to something, right? And usually what's it connected to? It's connected to other logic gates, right? I mean, because that's how chips are made. It's a bunch of gates all connected to one another, right? Output of gates are connected to the inputs of other gates, right? What are the inputs to the other gates? They're the gates of transistors, right? And so really what you're doing is when you switch the output, when Y switches from 0 to 1 or 1 to 0, basically what you're doing is you're charging or discharging the output, whatever this is connected to on the output, right? And initially when you first switch it, it's going to put a big voltage drop on the pull up or the pull down until it charges or discharges whatever it's connected to on its output, right? So in steady state, generally you don't have that much drop over either one of these transistors. When you're pulling up, if you're pulling up or you're pulling down, usually you're not dropping a lot of voltage over either the pull down or the pull up. But when you first make that change, when you transition the state of this transistor, you will have a big drop initially, right? You'll see so you'll ask a lot of these transistors in terms of the voltage difference right after you switch dynamically. So that's the problem, is that if you try to drop a lot of voltage, right, over this guy, what ends up happening, and this is kind of, I always find this interesting. So I mentioned that, again, when the transistor's on, the channel becomes decoupled. You have to look at the voltage, the average voltage across the channel, right? As long as the source and drain are about the same voltage, right, then the gate source voltage is going to be about the same as the gate drain voltage, meaning the voltage between the gate and the channel is about the same all the way across the channel. However, if you try to drive a big load, meaning a big voltage difference, you try to send a lot of current through this guy, what ends up happening is the gate source difference will be exceeding the threshold, but the gate drain voltage won't, right? Because remember, the problem, again, you have to look at the average voltage across the channel. If there's a big difference between the two sides of the channel in terms of the voltage, then what ends up happening is that this side of the channel, between the gate and near the drain over here, it'll become pinched off because the drain is really high. The drain voltage is a high voltage that's going to be close to the voltage of the gate, right? So the difference, the voltage difference between the gate and the drain, or at least in this half of the channel, is going to be small. So small, it might go under the threshold voltage, right? But the difference between the gate and the source voltage, yeah, that's no problemo. But what ends up happening is you get a channel that gets squeezed because over on this side of the channel, you have a bunch of charge carriers here because the electric field on this one is going to bring up these electrons. But there's no electric field on this side because the difference between the gate to drain is not enough. You might say, why isn't it enough? It's because you're trying to drop too much voltage over between the gate and the source and the drain, right? That's the problem, is that, again, the problem is the channel. It's what's the channel voltage? The channel voltage is going to depend on the source and drain. If the source and drain are too separated in terms of voltage, you'll pinch it off. And so that's what's called saturation mode, right? So basically what happens is that as long as you're not trying to drive that much of a load on the transistor, and as long as the gate is above the threshold, you're in linear mode. This guy acts like a resistor. It's just a resistor. It'll have a given resistance value, whatever your on resistance is, right? However, if you start to load this guy up and demand more and more current from him, what does it mean? If you're going to demand more current, it also means the drain source voltage is going to grow, right? Because you have to have that because of Ohm's law. If you want more current, you got to have these guys at a bigger and bigger potential difference. As you do that, the gate to channel voltage on the high voltage side of the transistor starts to go below threshold and it pinches it off. And what happens there is that the transistor stops being linear. It goes into saturation, which means that it will become a current source, basically. It'll just send a fixed amount of current. Even if you keep increasing the voltage on it, it's just going to give you a fixed amount of current. It's going to peak out. And that's called saturation mode. Does it make sense? Now you might say, why is this important? Well, as I mentioned, the reason this is important is because the performance of digital circuits, it depends on really two things. The first thing is the gate capacitance. The gate has capacitance. It takes time to charge a gate, right? Because it has to. It's a capacitor by its very nature. But the other thing is even once the gate turns on, the speed at which at which you can toggle the output of the transistor is also going to depend on the ability for that transistor to charge or discharge whatever's connected to its output as fast as possible. And that's going to be determined by the transistor width, right, as well as the saturation point on the transistors when it saturates, which ultimately is determined by the saturation point is going to be determined by the transistor size, the technology of the transistor, like how thick the oxide is between the gate and the channel, and the voltage going in the gate, which is normally always just VDD or zero in digital circuits, but it doesn't have to be. You can actually have the voltage. It's an analog voltage, so you can, as long as if you're above the threshold but below VDD, you'll get different behavior out of that transistor in terms of when it saturates. You guys with me? Okay, so I'll finish this lecture on next Monday, and then I'll go over the last few quizzes, and then we'll have a review. If you have any questions about the material, let me know.